I'm Miguel, and together with Mohammed, we'll be talking about Califorms. Califorms enables an efficient solution to the long-standing problem of memory safety. It does so with a simple modification of how data is stored in a cache line. Why should we care about this aging memory safety problem? Well, the lack of memory safety is a serious problem. People can be discriminated against, spied on, and targeted due to memory safety vulnerabilities. Unfortunately, this problem remains as current today as it has ever been. The reality is that memory safety vulnerabilities are very easy for developers to introduce unwittingly. So just what is memory safety? Put simply, it's when you access memory in an unintended way. Think back to any time you mistakenly overflowed a buffer or forgot to free memory. To put into context just how common these vulnerabilities are, consider that 70% of all CVEs in Microsoft products each year are memory safety related. And not to pick on Microsoft, but open source software doesn't fare any better, with over 29% of bugs found by Google's OSS fuzz being memory safety related. But what makes the issue so prominent is that attackers love memory safety vulnerabilities. Data about CVEs exploited in Microsoft products show that the overwhelming majority are memory safety related. So what can we do about this? A number of solutions have been proposed over the years, but they haven't been practical enough to be realized in commodity devices, whether it be because of performance or complexity. Califorms is different. It provides low overhead, robust security, and is compatible with legacy software. It is also easy to implement at the microarchitectural level and can be deployed across many devices. We build on a concept known as blacklisting. The idea is to insert tripwires randomly throughout memory, going off if an attacker trips on them. The technical challenge lies in how to efficiently identify these blacklisted locations. The straightforward approach to identify any byte as blacklisted needs 1 bit per byte. But this can lead to prohibitive memory and runtime overheads. Califorms instead moves the necessary metadata inside the program memory. This allows it to get away with just a single bit per cache line, drastically improving performance. For the rest of the talk, we'll first dive into the details of Califorms, highlighting its security and performance benefits. We'll then touch on related work and how Califorms fits in with other memory safety techniques. Finally, we'll conclude with some key takeaways about our solution.
Hello everyone, I am Mohammed and I'm going to describe to you how Califorms actually works. The key insight is to change how data is stored in cache lines. Let's start with an example. We refer to a cache line as normal if it has no blacklisted locations at all, like the one shown in the figure. Now, let us imagine a cache line with some blacklisted locations. In this case, one simple way to identify those locations is to use a single bit of metadata for every normal byte. This is called bit vector format, and it has the benefit of fast lookup. However, it also introduces 12.5% memory overhead. In Califorms, we store metadata about the blacklisted locations within the blacklisted locations themselves. How do we do that? We first compress the regular data in one part of the cache line, then we use the other part of the cache line as a Califorms header, in which we store the addresses of the blacklisted locations using some special encoding. In order to disambiguate between the blacklisted cache lines and the normal ones, we extend each and every cache line with one additional bit. This bit is set to 1 for blacklisted cache lines and is set to 0 for normal ones. Now, in order to enable Califorms at the system level, we need to do a few changes. Let's start with the microarchitecture ones. We modify the microarchitecture as follows. First, we extend the L1 and L2 caches in order to adapt our new cache line formats. Remember, our design goal is to keep the common case fast. So in L1, we use bit vector Califorms, the one with a single metadata bit per every normal byte, in order to guarantee fast lookup, resulting in a 12.5% memory overhead. On the other hand, for L2 caches and beyond, we only add one metadata bit per the whole cache line, resulting in 0.2% memory overhead. Similarly, we use the 1-bit Califorms in DRAM. However, we make use of the spare ACC bits to store our additional bit for every cache line, so that we do not add any further complexities to DRAM designs. As the size of L1 cache is much smaller compared to L2, L3, and min memory, the overall memory overhead is dominated by the 0.2%. As cache lines are moving between L1 and L2 caches, we insert two converters in order to switch between our two Califorms formats in both directions. So, how does that happen? Let us assume that a blacklisting instruction is issued by the CPU in order to blacklist a few bytes. In this case, and within L1 data cache, the bit vector Califorms will be used for fast lookup. And only when the cache line is spilled out of L1 to L2, we will convert the line format to the 1-bit Califorms. In L2, only one metadata bit is needed, same for DRAM, and that's why no converters are needed at that point. Please note all of these described changes are equally applicable to both 32 and 64-bit systems. In addition to our hardware changes, we add a new blacklisting instruction, write a couple of compiler passes, and modify the memory allocator. For more details on these aspects, please refer to our paper. Now, and to summarize, we note that Califorms has the following interesting properties. First, it has no false positives. In other words, it supports precise information storage, as it can handle from 0 to 64 blacklisted locations per cache line. Second, it supports existing performance optimizations, such as critical word first. Finally, it can be easily integrated into existing microarchitectures. For example, it doesn't disturb coherency. Now, let us talk more about the performance cost of our technique. Califorms performance overheads are mainly due to two sources: our hardware modifications that are needed to support the Califorms, and the way we handle the blacklisted bytes in the program memory. The results of our VLSI implementation showed that our hardware modifications have no impact on the cache access latency and can be totally hidden within the pipeline. The amount of blacklisting does affect performance, and in order to quantify this effect, we need to first understand the different insertion policies that we use for adding blacklisted bytes. Our compiler pass had three distinct policies for inserting tripwires. Our first policy, which we refer to as the opportunistic one, only makes use of the naturally occurring dead bytes or paddings within a struct. For example, the ones that exist to satisfy language alignment requirements. The second insertion policy, which we refer to as the full one, adds randomly sized tripwires between each and every field of a struct. Our third and last insertion policy, which we refer to as the intelligent one, adds tripwires only between those fields which are more prone to exploitation, such as arrays, data, and function pointers. Now, we are going to describe our evaluation methodology for those different insertion policies. First, and while our program is running, our new blacklisting instructions have to be invoked by the memory allocator in order to pass the blacklisted locations information from software to hardware. In order to emulate the effect of these blacklisting instructions, we add dummy store instructions that write some value to the corresponding blacklisted byte in the cache line. This allows us to use real machine for our evaluation instead of relying on microarchitecture simulations. So, we use a robust machine with Intel Skylake-based processor. Finally, we use this big 2006 benchmark suite with reference inputs. We run all of our experiments to completion. Now, we are going to show you the slowdowns for using those three policies. First, we show the results for the opportunistic policy. The average slowdown in this case is almost 8%, as shown in the bottom figure. But what would happen if we use this full policy? Remember, this is the one that inserts randomly sized tripwires between each and every field of a struct. In this case, the average slowdowns will increase to almost 14%. Finally, we show the results for the intelligent policy, and the average slowdowns in this case are only 1.5%. So, as the results show, the intelligent policy provides the best performance security trade-off, as it can protect all the security critical fields with less than 2% performance overhead. Now, let's talk more about the security benefits of Califorms.
To ensure Caliform security benefits, it's critical that blacklisted locations be placed unpredictably. Otherwise, an attacker may bypass them. Generally, the attacker's probability of success depends on the total number of blacklisted locations versus the total amount of allocated memory. This, though, is an approximate view. It doesn't take into account other key factors, such as the diversity of objects or general layout of memory, which the attacker needs to identify first. Given that this would be complex to generalize, instead, let's focus on the rare, best-case scenario for an attacker. The rare instance in which there's only a single object in memory. There, the attacker only needs to traverse an object's fields in order to find what they want to disclose. Now, because we insert 1 to 7 byte wide tripwires, the attacker needs to guess in which of the 7 possible offsets they can find the field of interest, or a 1 in 7 chance of succeeding. And the more fields the attacker is interested in, the harder it gets, compounding the 1 in 7 probability. Now, a natural question to ask is whether the attacker can make their lives easier by just disabling the blacklisted locations using the same mechanism used to enable them. The answer is no. To do so, the attacker would first need to bypass Califorms. That is, they have to exploit a memory safety vulnerability, scan for the necessary gadgets, and actually use them. Now, to see this more concretely, let's walk through an essential part of every attacker's workflow, a memory scanning attack. We start with an attacker controlling a pointer P, trying to find the password located somewhere in memory. The struct of interest is padded with Caliform tripwires, as is the unallocated memory. Upon scanning memory, the attacker lands on a tripwire in an unallocated region, triggering a Califorms exception, causing the program to terminate. They try this again, this time landing in a tripwire between 2 fields, and it's in this way that Caliform provides intra-object memory safety. Understanding both the security and performance benefits of Califorms, we are now better suited to position it against existing techniques. Base and bounds techniques, like Intel's MPX, rely on storing 2 additional words, namely the base and bounds, as metadata for every pointer. This leads to additional accesses to this metadata on every pointer dereference. Fat pointers instead rely on increasing a pointer's width in order to embed the metadata within the pointer itself, and this makes pointer operations significantly more expensive. Now, in contrast to these, Califorms may add additional bytes to objects depending on the insertion policy, and as a result, Caliform's performance scales according to how often blacklisted locations change during program execution. Now, as we've emphasized in multiple ways, Califorms is not only simple, but architecture with agnostic. It can be applied to a wide variety of systems, making it well suited for everything from servers to resource-constrained IoT and CPS. We believe Califorms thrives across this entire spectrum as it is easy to implement, has low overheads, and offers robust security. For more details on topics we couldn't cover during the presentation, we encourage you to read the paper. Thank you for listening.